Hey guys, welcome back to General Chemistry. Today we're going to continue on in Chapter 6, and we're going to look at our first application of that molarity equation to a problem that's called dilutions. So in any laboratory setting, so biological, chemical, whatever, we order solutions as stock solutions. So these are very, very high concentrations that are commercially available. But the problem with high concentrations is they're not very usable in a lab. So for example, hydrochloric acid comes as a 12 molar solution. If I were to use 12 molar solution in the chemistry lab, one, it would be very dangerous. So any drops on the skin could hurt pretty bad. And two, it wouldn't be very useful. It would just kind of eat through anything that we mix it with. Same thing if you're in a biology classroom, you put 12 molar hydrochloric acid on any biological sample and it's just going to destroy it. It's going to eat right through it. So while high concentrations are beneficial when we're selling things commercially, it's not terribly beneficial when we're actually doing stuff in the lab. So what we have to do is we have to dilute these materials down. So I have to take a little bit of the hydrochloric acid, I have to mix it with a whole lot of water, and I get what's called a diluted sample coming out. So dilution is a process where the concentration of a solution is lessened by adding a solvent. So the solvent in this case would be water. So we add a little bit of hydrochloric acid, mix it with a whole lot of water. Now the concentration of the hydrochloric acid has been decreased and a lot more user-friendly. So here's kind of a pictorial representation of that process happening. So you can think of this beaker as being the concentrated hydrochloric acid. So I'm going to take a little bit out, and of course it's a very measured value, and we'll talk about how to calculate that in just a moment. But it's a very measured value that I take out of my concentrated solution. Typically we put them into something called a volumetric flask. So here is that very concentrated hydrochloric acid going in. I know it's concentrated because if these blue dots represent hydrochloric acid, there's a lot of them in that little circle. So this volumetric flask has one job, and its one job is to measure 250 milliliters. So we're going to put our stock solution in here, and then we're going to fill up this this volumetric flask until it hits that line, and I know without a shadow of a doubt that there's 250 milliliters of solution in there. Okay, so here we are adding the water, and we have a new solution. Now I can see that this solution is much more diluted. So if I look in the same area, so let's assume these bubbles are the exact same size. If I look in the same area, now I only have 3 blue dots, where before I had a whole bunch of blue dots. So this is our concentrated, we add water, it becomes diluted. So the concentration goes down. The number of solute particles for a given area goes down. Okay. So I'm just going to real quick kind of derive the dilution equation, and then we'll just use that dilution equation moving forward. So we said that molarity is defined as follows. So molarity equals moles per liter. Oh, that's really bad. Moles per liter. If I were just to rearrange this equation, so I'm just going to do a quick algebraic rearrangement. So multiply by liters, liters on top, liters on bottom, over here. So just a quick algebraic rearrangement, and we get the following equation. Okay, so the amount of solute in moles is equal to molarity times liters. So why in the world would I rearrange it like that? Well, it's going to help us when we get to our dilution equation. Okay, so with a dilution process, we're going to have some initial time. So we'll call that time before. So that would be this example here. Would be the concentration of that stock solution. So that's going to be before we dilute it down. That's going to be its original value. And we're going to have some later time, so we'll call that time 2. We're going to have some later time, and that's going to be after it's diluted. So again, if we go back to our example, this would be our second. So that would be after it's diluted. There's a volume associated with that. There's a molarity associated with that. Okay. So we have some initial time before we dilute everything down. We have some final time after it's been diluted. And these two equations are going to help us put together a formula. Okay. So here's kind of the important piece. Here's the trick to deriving this equation. Since the dilution process does not change the amount of solute, we can set N1 and N2 equal to each other. So when we take that concentrated solution out, okay, so I could take out 2 moles of hydrochloric acid. I am then going to take that 2 moles and I put it into a volumetric flask. So in here we'd have 2 moles of the hydrochloric acid, right? And then I simply fill it with water. So I take 2 moles out of my concentrated, I put 2 moles into my diluted. That number of moles doesn't change, it stays the same. So if we can set those two numbers equal to each other, then we are able to derive the following equation. So if we had N1 equals N2, and that was equal to M1 L1, and this was equal to M2 L2, what we can essentially do is kind of drop this middle part of the equation, and now we have our equation for a dilution. Okay, so that was just a quick derivation. Am I going to ask you to derive this equation on a test? Absolutely not. What I'm going to ask you to do is use this equation to solve a problem. So M1, L1, this is going to be our initial time. So before anything was diluted down, you can also think of this as our concentrated solution. So molarity of the concentrated solution, the volume of the concentrated solution. M2, L2 is going to be our final. So after we added the water, we filled it up. What is the molarity in liters of the final? You could also think of this as the diluted solution, right? So the algebra and the math of these problems is not terribly difficult. The hard part is just making sure that we get all the pieces into the right spot. So let's take a look at an example together. We have a 0.85 liter solution of 5 molar copper nitrate. It is diluted to a volume of 1.8 liters by the addition of water. What is the molarity of the diluted solution? So again, with any equation type problem, I like to take inventory of what we know, what we're trying to solve for. So we have M1, we have L1, and then we're going to have M2 and L2. Okay. So I'm just going to read back through the problem and try to figure out what goes where. So we have 0.85 liters, 5 molar solution, and that is going to eventually be diluted. So that tells me this is my concentrated solution. Okay. So that's M1, L1. So we've got 0.85 liters. We've got a 5 molar solution. All right, so we keep reading the problem. It is diluted down, so that's now I know I made the transition to a volume of 1.8 liters. So that's going to be our volume when we end. And we want to know what is the molarity of the diluted. So this is what we're solving for. Okay. Once we have all of our pieces in the correct location, now it's just simply plug and chug through the problem. Plug it in, crunch the numbers. So M1 is 5.0 molar, L1 is 0.85 liters. And then M2 is what we're solving for, and L2 is 1.8 liters. Okay. So now just an algebraic rearrangement to solve for M2. So I divide by 1.8 liters. Whatever I do to the right side, I also have to do to the left side. So divide by 1.8 liters. Here I want to take a pause and look at my units. So I have liters on top, liters on bottom. Those cancel. I'm left with the unit molarity, which is handy because that's exactly what we're solving for. All right, so now crunch it out. We're going to multiply on the top, divide by the bottom. So 5.0 times 0.85 divided by 1.8, and we get 2.36 molar. Okay. The last thing we have to ask ourselves is, does this make sense? You kind of always can predict what the answer is going to be. So does it make sense? If M1 was our concentrated, the molarity of the new solution should be smaller or lower than 5. And it is. So we started at 5 molar, we went down to 2.36 molar. That makes sense, right? The other thing you can keep an eye on are the liters. So if you'd have to solve for maybe one of these. The original L1 is always going to be a smaller number, and L2 is always going to be a bigger number. That will always hold true. So when you're looking at comparing those two numbers and saying, well, does this make sense? That's what you're looking for. Okay. So this was our first look at dilutions. Again, this is a skill I need you to go and practice to get good at it. I hope you guys found this helpful.